Hello, my name is Colin.
My name is Evin.
My name is Dylan.
My name is Hannah.
My name is Arsa.
And we are SPARC! This issue began with the decline in petroleum production, prompting the government to seek solutions such as increasing the production of electric vehicles, which require energy storage media, one of which is lithium-ion batteries. Research in electric vehicle production has driven the lithium-ion battery industry to innovate and scale up manufacturing. Graphite is an anode material used in lithium-ion batteries. However, to keep electric vehicles affordable for the public, high-quality yet cost-effective graphite is needed. At the same time, Indonesia's oil palm plantation generates a very high amount of solid waste, dominated by empty fruit bunches or EFB, which account for about 30% of total biomass waste.
We see this as an opportunity for innovation in lithium battery anodes by utilizing EFB as a source material for battery-grade graphite.
Our palm biomass contains cellulose and lignin, making it a suitable carbon precursor for graphite production.
Because of that, we developed an innovative solution which is sustainable palm waste derived anode for rechargeable lithium-ion cells, or shortened as SPARC.
SPARC consists of palm waste-based anode and is a secondary battery which is rechargeable.
This battery has several components. Positive case is the bottom part of the metal case that functions as the positive terminal and holds the internal components in place.
The spring maintains strong electrical contact with the device.
Spacer is a metal component used to fill internal space and ensure other components are compressed correctly.
Cathode is the positive electrode where a chemical reaction occurs to generate electricity.
Sputter is placed between the anode and cathode to prevent short circuits while allowing the movement of ions through the electrolyte.
Anode is the negative electrode that we made from oil palm waste, functioning as the site of oxidation and electron release.
Negative case, aka the top part of the metal case, that functions as the negative terminal and is tightly sealed by a gasket to prevent leakage.
The first step is to prepare the equipment, including scaling our raw material, which is palm oil waste, with a high precision weighing scale.
Next, we carbonize the material in a tube furnace at 800 degrees Celsius for 2 hours.
After that, we take out the carbonized material from the furnace tube and grind it using mortar and pestle until it becomes a fine powder.
The carbon was then added to the solution and mixed with a solution containing ferric chloride hexahydrate for 24 hours at 80 to 90 degrees Celsius.
Next, we separate the paste from the liquid, then dry it for 24 hours until it forms from paste to more solid powder, which is then placed in the oven.
The next step is to grind it again with a mortar and pestle to ensure a smooth texture.
After this, we proceed with the pyrolysis process in a furnace at 1300 degrees Celsius for 2 hours, increasing the temperature by 5 degrees Celsius per minute, and then we store the resulting material.
Pyrolysis is the process where biomass is heated without oxygen to produce carbon-rich materials.
Next, we weigh the material and prepare 2M HCl. We slowly mix the palm oil waste paste with 2M HCl and stir it, allowing it to sit for 24 hours.
We then separate the solid from the liquid. After that, we wash the solid with water, stir it, let it settle, separate the liquid, and replace the water.
Repeat the cycle for at least 7 times until its pH reaches neutral.
And then we compact the washed product.
Next, we dry it in the oven again.
Finally, we grind and sieve it until it passes through a 325 mesh filter.
The produced graphite was characterized using several material analysis, including X-ray diffraction, Raman spectroscopy, and high-resolution transmission electron microscopy.
After producing the anode-grade graphite, we proceed to fabricate the battery cell.
The first step is to add N-methylpyrrolidone polyphenylidene fluoride as binder and the carbonized EFP material.
Next, we spread the anode graphite slurry onto a copper foil collector or copper foil.
After that, we pass it through a calendering machine. And then we place the copper foil in an oven to dry the electrolyte.
Next, we cut the dried anode-coated copper foil into a square shape, and then press it with the die cutting machine to form a circular electrode.
We then move the components into the glove box.
The coin cell battery is assembled inside the glove box because oxygen and moisture must be excluded, because exposure to this can degrade the materials or potentially cause a fire.
From testing graphite material with Raman, XRD, and HRTEM, it shows that graphite material can be produced through catalytic graphitization at a relatively low temperature, which is 1300 degrees Celsius. Electrochemical testing of battery anodes shows a specific capacity of 170 mAh per gram.
Our product has more ability than your conventional battery.
Our product consists of 5 features certain as green: G as greater efficiency, R as reliable performance, E as established technology and established cycling, N as net impact reduced.
And that is our battery innovation! SPARC is the flagship product that we hope will be adopted by major companies in the battery industry to support a more sustainable Indonesia and to serve as one of our steps in contributing to Indonesia's progress toward the sustainable development goals, particularly responsible consumption and production.
Lancung makan opor di kereta.
Malaysia pula menikmati lauk ikan.
Terima kasih kerana mendengar kata. Moga kita gemilang di masa hadapan.